Let us look at another problem which also deals with the normal and tangential components. So the motion of a particle is defined by the equations x is equal to 2t plus t squared and y is equal to t squared. We asked to determine the normal and tangential components of the particle's velocity and acceleration when t is equal to 2 seconds. Again, the very first step is to write down what we know. We know that we're dealing with the normal and tangential framework. We're also given the position in terms of time. So we have r is equal to xi plus yj, which is equal to 2t plus t squared I plus t squared j. We also know the fundamental equations in vector form. V is equal to dr over dt and A is equal to dv over dt. Remember, we need to find the normal and tangential components of the particle's velocity and acceleration. But the very first step, before we start working on that, we need to find expressions for v and a as a function of time. So to do so, we need to find vx and vy. So vx is equal to dx over dt. We simply take the derivative and get vx is equal to 2 plus 2t. Taking the derivative of y, we get vy is equal to 2t. Then we can find the magnitude of v by simply replacing t by 2, since we want to find the value of v at t is equal to 2 seconds. Replacing all that, we get the value v is equal to 6i plus 4j. Now to get the magnitude of v is equal to square root of 6 squared plus 4 squared, which is equal to 7.21 meter per second. And if someone wants to find the direction of v, we can write that theta, which is the angle with respect to the x-axis, is equal to tan inverse of vy over vx. Remember, to get the angle with respect to the x-axis, it's always equal to the inverse of the tangent, in which vy is divided by vx. And so we end up with the value theta is equal to 33.69 degrees. Now you might be wondering why we're calculating the magnitude of v. Well, remember, we know that an is equal to v squared over rho, so it is important for us to know the value of v at that specific instant in magnitude. And since v is always tangent to the path, we know that v only includes a single component, which is vt. And so vt is equal to v is equal to 7.21 and vn is equal to 0. So now we know that the t-axis in the normal and tangential component is collinear with the velocity vector. And we now know the direction of the velocity vector with respect to the x-axis, which makes an angle of 33.69 degrees. Now similarly, to find an expression of a as a function of time, we simply need to take the derivative of v, which gives us 2i plus 2j. Then to get the direction of a, we need to take the tan inverse of ay over ax, which gives us 45 degrees. To find the magnitude of a, we take the square root of ax squared plus ay squared, which gives us 2.828 meter per second squared. So now we have the magnitude of a and its direction. So we can draw the vector a in the graph. So we know that it makes 45 degrees with the x-axis, and we know that the t-axis makes 33.69 degrees with the x-axis. We can now find the angle that a makes with the t-axis. So to solve for an and at, we need to find that angle, because remember, we know that an and at are the projections of a on the n and t-axis. So if we know the angle between a and the t-axis, we can simply take the projection by applying trigonometry. So we know that alpha, which is the angle between a and t, is simply the difference between the angle of a with x and the angle of t with x. And as we have said earlier, the angle between t and x is the same as the angle between v and x. And so this gives us alpha is equal to 11.31 degrees. Now that we have the angle, we can simply apply trigonometry. So an is equal to a sine alpha, since we want to get the side that is opposite to the angle. So 2.828 times sine 11.31 degrees gives us a value of 0.555 meter per second squared. Similarly, to get AT, it's A cosine alpha, which is equal to 2.828 times cosine 11.31 degrees, which gives us AT is equal to 2.77 meter per second squared. So this problem is very interesting since we were able to jump from the rectangular coordinate system to the normal and tangential coordinate system. And to do so, we actually made use of the fact that the velocity component in the normal and tangential coordinate system is always aligned to the t-axis. So knowing the angle of v with respect to x, we can get the angle of t with respect to x, and then we can find the angle between the acceleration and the t-axis. Then take the projections and get an and at.